Okay. Should be ready to start. Sorry for the delay. So let me write back the equation from which where we got last time, which is just let me know if I'm using a different symbology, but I don't think so. Different symbols. This is a stochastic process. Then we said that this is autoregressive process. Or autoregressive model, more or less same thing. And order one. Okay, that's good. And hypothesis is in x is equal to 0 to x is Gaussian, and 3 mi epsilon equal to 0, epsilon is independent. Okay, this is where we got. Just 1 second, I'm trying to turn off the slide. Let me see. Okay, good. To turn on, sorry. Okay, so basically we are talking, as you know, of stochastic processes, and I understand that this is, as I said, a topic that is a bit nasty to study, and I promise that today I'm finishing it. And then afterwards, I also would like to get your opinion, but this is another story. And basically, what is a stochastic process is a family of random variables. And family because we are modeling x, and each time step has a separate random variable. So xt is a random variable, xt plus 1 is a random variable, and so on. So the stochastic process is a family of random variables, and this is the definition that you should learn. And I said that a striking property of this stochastic process is dependence. So basically we consider a set of random variables and not just one random variable, because there is dependence among these random variables that are observed at different times. So basically the presence of dependence is the reason why we introduce this complication. And I also said that we model this dependence through this linear relationship, which is very simple. So we devise a very simple relationship, which is linear, to take dependency into account. And I said that we measure dependence through correlation, and in particular by drawing the autocorrelation function. You know how to draw it. And I said that an essential requirement to accept this description, to say that this description is working, a requirement is that epsilon is independent, like it's written here. Because I said that if we introduce a relationship among the different random variables to explain their dependence, it's intuitive and essential that what remains from that linear description, the error from that description, is without any dependence, because the linear relationship has the task to explain dependence. And therefore, if the linear relationship cannot explain dependence, then it's not an appropriate relationship. And to close the circle, I said that for this relationship to work, is essential that xt is Gaussian. And the reason is that I mentioned that the Gaussian distribution is the only one distribution that is preserved through a linear transformation. I said that we also require that the mean value of x is equal to 0. And this is essential. I said this is not a very essential requirement. This is useful. because otherwise I should write this relationship in a different way. And then I said that given that x is equal to 0, also another requirement, I'm not sure I mentioned it, is that epsilon has a mean value of 0. So not only absence of dependence, but also the mean value of epsilon should be 0. And this is because, it's intuitive. Let me explain by saying that if the mean value of x is 0, the error, what remains from the linear relationship, should have the same mean, because what we expect from an error is that it fluctuates randomly through a value of 0. Otherwise, we would say that the model is biased or distorto in Italian. So this is what we expect from epsilon. Okay, so what are the basic questions that I may ask at the exam on this topic? I usually ask, what is a stochastic process? And you know what you are expected to reply. And I usually ask to introduce the autoregressive model of order 1. Order 1 because you will see what is order 2. I will introduce order 2 in a few minutes. It's very simple, a simple extension. But usually I ask what is an autoregressive process of order 1, and you are expected to write this relationship. And I also ask the assumptions. Remember that any time that you study something and there are assumptions, the assumptions are something that may be asked at the final examination, because assumptions are very important. When you apply a model, you have always to be well aware of assumptions. Okay, and then I may ask why the process is required to be Gaussian. If I see that you are good in replying to the previous questions, I may ask what if the process is not Gaussian, and you will see next hour what are the solutions, because I said that our variables in general are not Gaussian, so of course I need to devise something if I want to apply this representation to a non-Gaussian variable. And I may ask other questions that I will summarize later on when I finish. Okay. Now, basically, this is all what we need. Pay attention in your slides. There is a fourth assumption which speaks about cross-correlation. Just forget it. Because I decided this year not to mention cross-correlation because I don't want to make the whole stuff too complicated. And the fourth assumption is basically, I also decided not to mention it because, strictly speaking, it's already embedded in the third. So it's not necessary that I introduce the fourth assumption. It's useful, but not necessary. So just forget it if you look at the slides. And in general, when you look at the slides and you see something that I didn't mention at the lectures, don't be concerned. What I am asking is what I say here. And if you see any difference when I am at the exam, just let me know. If you feel that I asked a question that I didn't introduce in the lectures, it means that I am making, it means two possible solutions. One solution is that you are a very good student and I'm trying to ask you something that I didn't say. And in this case, I tell you, I may say, yes, I know that I didn't speak about this on the lectures, but try to reply anyway. And this means that you are in a very good position, so you should be excited if this happens. And the second solution is that I forgot that I didn't speak about this. So if you realize at the exam that there is something that I'm requiring, asking that you didn't have in your notes, just let me know. And it's not a problem, absolutely. And maybe that you are wrong, and then I tell you, because usually if I am mentioned, if I am told that there is something wrong, I get the perception of what are the topics that I mentioned in the lectures and what are not. Not to say that there is a video, so it's easy to check. Okay. Now, I think that an important information that I should give to you now is how to generate the synthetic variables. Let's suppose that we estimated this model, and you know how to estimate the parameters, because we spoke also of the estimation of phi1. And now, let's suppose that you estimated the parameters, how to generate synthetic data. And this is the last piece of information that you miss, because of course our final purpose is to generate xt. Okay? So let me talk now of generation of synthetic data. And let me say that when you get at this stage, you already estimated the parameters, phi1, and also it said that you need to estimate the behaviors of epsilon, and in particular you need, you know already the probability distribution of epsilon, and therefore what you need is to estimate the mean and the standard deviation of that distribution, because you know that the distribution is Gaussian. You also know that the distribution is zero mean, so strictly speaking, you just have to estimate the standard deviation of epsilon. So when you get to generation of synthetic data, you already know phi1, and you already know that epsilon is Gaussian, zero mean, and with assigned standard deviation. And also let me say that when you get to generation of synthetic data, you already checked all the assumptions. And this is implicit because, you know, if I say that you know everything of epsilon, this means that you already checked that epsilon is Gaussian, that the mean is zero, and of course you preliminary checked that x is Gaussian and that the mean of x is zero. And if not, you just make a transformation of x to get to the zero mean situation. Okay, so you already checked the assumptions and you know phi1 and everything of epsilon. Now, how to generate synthetic data then? The first step is to generate random outcomes from epsilon. This is easy. Why this is easy? It's easy because epsilon is independent. So you don't have to take memory into account. And you know, pay attention to this, you know that when a random variable is independent, you can generate just by sampling from the probability distribution. You use R norm in R, you use the function R norm in R, you specify in R norm the number of outcomes that you want to generate, the mean, 0, and the standard deviation, which you know. And pay attention, why R norm? Because it's Gaussian. So this is very easy. To generate epsilon, you have all means to do that. Not only you have the means, which is the function R norm, but you also understand what you are doing. You are sampling from a normal or Gaussian distribution. You are sampling the required number, capital N, of outcomes. You are sampling from the distribution that has zero mean because by assumption epsilon has zero mean. And you are sampling with the standard deviation that you know because you computed the epsilon. You know how to compute the epsilon because we did that last time. And then you computed the standard deviation of the obtained epsilon. So you not only are doing something, but you also understand. And if you are missing some detail, just let's discuss it, okay? So this is the first step. Let me write here. Generate epsilon t. Generate n outcomes from epsilon t. Okay. Now, second step. You have the epsilon, so we can generate x1, sorry. How can we generate x1? We just use the formulation of the model of the stochastic process. And be careful, you don't have xt minus 1. Why you don't have it? Because you start from 1, you don't have any previous observation. When you start your simulation, you don't have any previous observation. And then you have to guess it. And what is the best guess? It's 0 because it's the average. So let me say that x1 is 0 plus epsilon 1, which is known, epsilon 1, and also 0 is by assumption. By assumption, μx equals 0. Perfect. Now, third step, let me say that it's not the third step, it's 2 prime, because it's the same step I'm talking about. You generate x2. x2 is equal to phi 1 known, phi 1 is known, which multiplies x1 plus epsilon 2, and so on to n. So you see that it's very simple. It's so simple that you probably doubt that it's working. Let's see, okay? For sure it is. If you just look at the procedure, it's simpler than using a Reinforanoff model, for sure. But there are some differences which we will discuss, okay? Okay, that's good. So this is our simulation. And basically, you have a function in R for performing all these steps. R function, and this R function is lowercase arima.sim. So you can just, if you go and look at the help of R, you find an explanation. And you may wonder why this name Arima. I'll explain, okay? Okay, this is for the autoregressive model of order 1. This model is also called AR, as I mentioned to you, AR1. AR stands for autoregressive. Perfect. Okay, I could close here, but there is some additional information that I want to give you, and because you know, when I decided how to explain, how to introduce to you this topic, I thought that it's the best solution to get to the end of the story as soon as possible by introducing and by giving to you the minimum of the required information to understand how it works. Because my target is just to show that it's just an application of a linear regression. And the theory looks complicated, but indeed, you see, it's just an application of a very simple linear model. So I wanted to get at the end of the story. But as I told you before, my explanation was reduced to providing the minimum amount of information. Now I just would like, for your interest, and because you need also this for if you want to apply this model in practice. Now I want to give to you additional information. And let me classify this additional information into categories. There are some information on the theory that you still miss, which I need to give to you. Otherwise, you are missing two important pieces. So now I have some extension on the theory, which is not very complicated in my opinion, but we will see. And then there is another class of information which is extension of this model. And in both cases, I will not speak a lot. I will just provide to you what I believe is the minimum information that you need in order to get an overview of the topic and to be able to apply this approach. So let me start with some additional theoretical considerations, because there is something that I didn't tell you which is very important. Also, it's very important from a practical point of view. So, let me introduce a couple of concepts now. The first concept that I want to introduce is the concept of stationarity of a stochastic process. Stationary. And I put between parentheses stochastic process, because this is a concept that applies to stochastic processes. There is one problem here. The problem is that stationary has an intuitive meaning. If I asked you, what is your guess on the meaning of this theoretical concept, you would say something that doesn't change. When we say that a situation is stationary, like an ill person in the hospital, we sometimes say it's stationary, which means it's not improved, but it's not worsened. So it's something that is keeping at the same level, more or less. And this implies that in mathematics and statistics, some people provide a personal interpretation of stationarity by intuition. And this is a big problem, because when a theoretical concept, which is important, is misinterpreted, it's a problem, especially if we are engineers, because then when we make a design of a structure, we need to have clear what are the concepts and how they are defined. Okay, I try to better explain by making an example. Stationarity is often used with respect to climate and therefore with respect to engineering design. So very often today, you heard that climate is no more stationary, and therefore design methods need to be updated. And for instance, a practical consequence of this is that if you assume that a river flow regime is changing, it's non-stationary, because the climate is non-stationary, like there is an increase of probability of extreme rainfall, which translates in an increased probability of floods. This is called non-stationarity, and therefore people say, okay, this means that you can't use past observations to support your design. Because if you use past river flow data to support your design, then you assume that the past is representative of the future. But if climate is changing, these people conclude by saying that climate is changing, so the situation is non-stationary. You can't use past data to predict the future. So you see that the interpretation of the concept has important consequences in design. Basically, what do we do in hydrology? We use data to estimate models and to make design. We previously used rainfall runoff models. We are now using stochastic processes. In both cases, we are estimating our phi1, our epsilon, by using data. So, we are assuming that the data are representative of the future. Now there are interpretations which say that the past is not more representative of the future, and these interpretations imply that all these methods that I'm teaching to you are no more useful. So it's important to clarify two things. What is stationarity? So when one tells you climate is non-stationary, you can't use stationarity to support your design. You understand what people are talking about, and you understand if they are right or not. And the second thing that we need to clarify is it correct to use the data to support your design or not? Okay, first question, what is stationarity? Okay, let me just remind you that there is an intuitive interpretation, something that doesn't change. Now let's see how stationarity is defined in mathematics and statistics, and also in engineering. Because when you say, I'm using a stationary approach to design, you refer to the definition that I'm providing to you now. You refer to this, okay? So stationarity means that you deal with the stochastic process. This is something that people don't realize. So stationarity in mathematics and statistics is referred to with reference to a stochastic process, to a family of random variables. This is the first thing. So when one says climate is non-stationary, he's implying that climate is represented by a stochastic process. Unless he says, I'm not referring to stationary in a mathematical sense, I'm just referring to stationary in another sense. But if we refer to engineering, mathematics and statistics, stationarity refers to a stochastic process. And means what? Means that the probability distribution of the process is not changing over time. This is the definition. Let me write it. Look, if you go to Wikipedia and look for stationarity, you jump to definition of stationarity for a stochastic process, so it's correct in my opinion. And there is written that the joint probability distribution doesn't change. Okay, it's more precise. Let me say that I didn't introduce what is the meaning of joint probability distribution. I don't want to introduce it, so I'm providing to you this definition, probability distribution. I think it is correct anyway, because with probability distribution I can imply all the meanings, including the joint. But I just want to explain to you that if you go to Wikipedia, there is a different definition, looks different. In my opinion, they are similar. So what does it mean? It means that you have a probability distribution describing your process, and if you shift in time, the probability distribution doesn't change. I want to better explain. In practice, what it means. It means that if you go over the Po River and you look at the river flow in now, in April, you go the next year, again in April, and you see that the probability distribution is the same, which means that the average of the river flow is the same, which means that the probability of getting a flood is the same, the probability of getting a drought is the same, doesn't change in time. What is the implication? The implication is that if you analyze data of Po River flows collected 100 years ago, they are still representative of the probability of getting a flood, getting a drought, whatever. So it's perfectly reasonable to use this data to support your design. Okay, you may say, but if I go over the Po River in summer, the probability distribution is different with respect to going there in April or in October. So you may say, you may ask me, is then stationary the river flow of the Po River or not? I would say yes. Don't make confusions between change of the probability distribution and variability. So basically, the fact that the process is stationary means that, you know, the situation is the same that 100 years ago. Of course, you have some variability. You have, if the average of the river flow of the Po River is 1,500 cubic meters per second, and the average is computed in the longer period, like 10 years, stationarity means that the average from 1930 to 1940 was the same, was 1,500. Of course, you have some local variabilities, but then it's a change because a flood may occur, which is reversible, comes back to a normal situation. You don't have permanent change. So you may ask me, provide me an example of non-stationarity so I better understand. Yes, it's easy. Let's suppose that you build a dam on a river, then it means that downstream you have a permanent change of the probability distribution of the river flow. It's an example of non-stationarity. Because building the dam, you change everything. You change the probability distribution. Building a dam, you can release downstream a constant river flow. It means that it's deterministic. It's no more a random variable. So, of course, you change the probability distribution. Another example of non-stationarity is if you have a change in climate, irreversible. Because, you know, let's don't confuse, even when speaking of climate change, the variability, which implies that you come back after a while to a stationary situation, steady, let's say. Let's not confuse the variability with something that changes forever. Okay, then this is the meaning of stationarity. The problem with this interpretation is that people precisely confuse non-stationarity with variability. So sometimes when a flood occurs, people say, okay, this is an example of non-stationarity, while it could be just an example of variability. Perfect. Now let me say that this stochastic process can be stationary or not. And for instance, if you try to make a simulation with phi 1 in absolute value greater or equal than 1, and you plot it, you will see that the process is non-stationary. What does this mean? This means that the average, the mean value, departs from 0. Is no more constant. Instead, if you take phi 1 in absolute value lower than 1, this is stationary. Just try to make an experiment. It's very simple. It just suffices that you generate epsilon with whatever standard deviation, and you try to apply this simulation procedure that was written here before, and you try with two different values of phi 1. Try with 2 and with 0.5, and you see the difference. The difference is that one solution is non-stationary, the other one is stationary. And you will see that if you use phi 1 equal 2, you have a final result, a graph, that looks like this. If this is xt and this is time, you get something that looks like this. Always increasing, with maybe some step in which you get a decrease, but overall, the process is increasing. This is phi 1 equal 2. Conversely, if you use phi 1 sorry, equal 0.5, you get to a situation like this. You have some variability, you have some changes, but then you go back to zero mean situation, to the zero mean situation. Okay, now, second question that I mentioned to you. Is it appropriate to use the data, past data, to support your design? So, are our processes, hydrological processes, stationary or not? My interpretation is yes, of course it is appropriate. And then I suspend, but just let me clarify to close this concept. Yes, it is appropriate, as I said, to use past data to support your design. And for one very simple reason, because there is no other solution.